Okay, so do you have any doubt from last class?
No, sir.
Okay. So we have derived this particular part, mechanical potential energy stored in a wire. Now let me define you. If you rearrange this particular equation to convert in terms of force, just see. In this part, I have written F equals to YA divided by L times small y. And since small y is almost comparable to small l, so we can write F equals to YA divided by L times y to be YA divided by L times small l. So we can rearrange this expression as U equals to half YA divided by L. L square will be L times L. This particular quantity will be termed as force, and this small l will be termed as extension. So we can write half into force into extension. Noor, is it clear?
Yes, sir.
Okay. Now, if you have to convert this particular expression in terms of stress strain, so let me define you how to convert it. We can write U equals to half F multiplied by L. If we divide this expression by same quantity and multiply it by same quantity, then this fraction will remain same. So I've just multiplied and divided by volume to this particular fraction. So it will become F times small l divided by volume, which is area times length times volume.
Sir, why
This
did you divide it by volume and multiply by volume?
to convert it into some other quantity.
Okay.
Just see, we have F divided by A, which is also equals to stress. This is small l divided by capital L, which is also equals to strain. So we can write this particular expression as half times stress into strain times volume. So this will be another relation to find potential energy stored in this wire. Is it clear?
Yes, sir.
Okay, just write it down.
Sir, I'm done.
Now, there will be some question related to this particular chapter. One is Poisson's ratio. Suppose you have a rod having length L, area of cross section A, or let's say diameter of this particular rod is L. So if you apply any deforming force on this particular rod to elongate it, on elongation, there will be decrease in its width like this, so that volume of this particular object remains same. Okay, Noor?
Yes, sir.
Suppose you have a clay which is in the shape of cylinder, and if you have to elongate it into further elongated length, so width of that particular cylinder may get deformed to some small width so that its length gets elongated. So you can conclude on extending its length, width decreases so that volume of that object remains same. Similarly, in this part, since we have to elongate this rod to this part, due to which there is decrease in its width from its actual diameter d to this diameter, which is d minus delta d. So in this part, there is two different types of deformation in this object. One is along its length. We call it as longitudinal strain, which is equals to delta L divided by L. And the next term is along its width. So we can relate, or you can call it as lateral strain, which is equals to change in its diameter divided by initial diameter, or which is further equals to change in its radius by its initial radius. Since diameter of this particular rod is decreasing, so we put negative sign in place of it. Is it clear?
Yes, sir.
So in this part, we have mainly two different types of deformation. One is along its width, that is called lateral strain, and the next is along its length, which is called longitudinal strain. So if you take the ratio of these two terms, lateral strain divided by longitudinal strain, this ratio is called Poisson's ratio. So Poisson's ratio equals to lateral divided by Poisson's ratio is represented by sigma, which is equals to delta D divided by D whole divided by delta L divided by L with negative sign. Or you may write in terms of radius as delta R divided by R with negative sign whole divided by delta L by L. Since this longitudinal strain or lateral strain will be unitless quantity, and the ratio of these two terms, which is Poisson's ratio, will also be unitless quantity. So you'll say this particular sigma is unitless quantity. Now, if you have for perfectly rigid body, elongation or compression will be 0. So in that case, modulus of elasticity, Young's modulus, bulk modulus, shear modulus will be infinite. So Young's shear bulk will be infinite, and Poisson's ratio will be just equals to 0.5. In general, sigma lies in between -1 to less than 0.4 or 0.4 to 0. This is theoretical value, and this is practical value. Noor, any doubt?
Sir, can you just for perfectly rigid body, that one, can you read the sentence again?
Okay, just 1 minute. Suppose you have any perfectly rigid body. So is there any elongation in that particular rigid body? So you'll say no. Delta L should be equals to 0 or delta V should be equals to 0. According to the formula, Young's modulus equals to F times L divided by A times delta L. So if you put the value of delta L to be 0, this part, so you're left with 1 divided by 0, and 1 divided by 0 is nothing but infinite. That's why Young's modulus becomes infinity. Similarly, in case of beta, which is equals to P times V divided by delta V with negative sign, since delta V in the case of perfectly rigid will be 0, so this particular quantity will be 0. So 1 upon 0 or any quantity divided by 0 is nothing but infinite. That's why Young's modulus, shear modulus, bulk modulus becomes infinity. Is it clear?
And the sigma is always equal to 0.5.
In case of perfectly rigid body,
Okay.
for which there is no deformation, no change in its volume, no change in its dimension. Okay?
Yes, sir.
Okay, just write it down.
So I'm done. Can you please scroll down? So I'm done.
Next is you must have used Thermocol for various school projects.
Yes, sir.
So can you tell me what is the main purpose for which Thermocol is being used? Is it for just school project or something else?
Of course, not only school projects, but I don't know where it is used.
Okay. Just consider in your house, there is, or you purchase some
Also,
PC,
yes,
television.
yeah.
So thermocol, along with that electrical gadget covering from its entire all boundary in its own packing. So what is the main purpose of using that thermocol while it's packaging?
Protection.
From which part?
Protecting the electronic gadget.
Protection from what? From
From
any germ during
surrounding.
its traveling. Okay.
Yeah.
So those substances are called elastomer. Let me define you its behavior. If you plot stress versus strain curve for those substances, this is stress and this is corresponding strain. So if you compress thermocol to a particular point like this and release it, it tends to acquire its original shape or tend to go back to acquire its original shape like this. So on elongation or on compression, graph will be like this. And then on returning back to acquire its own shape, the curve will be like this. This maximum point up to which there will be no breaking is called saturation point. And if you compress that particular substance to beyond this saturation point, it may break. Okay. So the substance which having only elastic limit, no plasticity, no anything further for this stress strain curve are called elastomers. Those substances are mainly used for shock absorbing substance during traveling for any jerk. Okay.
Yes, sir.
So elastomers are the substance which having only elastic behavior beyond which they may break. These substances are called or termed as or used for shock absorbing. So greater the area of this particular curve for those substances, they will behave as good shock absorber. Greater the area of stress strain substance will behave as good shock absorber. Noor, is it clear?
So I understood this. I just didn't understand the graph.
Okay. Suppose if you elongate that particular substance or compress to a particular instant, it may follow this particular curve for its elongation part. So stress will be at this point and corresponding strain will be at this point. On further elongation, stress will reach to this and strain will reach to this. On further elongation, it will reach to its maximum value. Let's say this. So on compressing, they may follow different behavior, stress versus strain. In first part, stress is increasing at larger proportional as compared to strain, while coming back, strain is decreasing as lesser proportionality as compared to a stress. So you will say in this particular curve, stress and strain are not behaving as similar while elongation or while compression. There is some lagness between them while stretching and while compressing back. Is it clear?
Not really.
Okay, just 1 minute. Suppose you have a rubber band. Like this. Okay. You must have used a rubber band for various purposes. Okay, suppose you fixed it at this point. Now, if you elongate it, it may elongate to a particular distance like this. And if you stretch it beyond it, it may get break. Okay.
Yes,
So
sir.
this particular rubber band is also termed as elastomer. So while elongation, you have applied some stress to this particular object and corresponding elongation is up to this part. Okay, any doubt?
No, sir.
Now intend to return back to its original shape. So on stretching, you must have applied that much amount of stress very rapidly to go from this end to this end. But in coming back to attain its original shape, it may take some time and it may get slowly deform or slowly acquire its original shape. So we can say the rate of change in stress and strain while elongation is not the same while compression. Is it clear?
Yes, sir.
That's why these two lines are in differ. Or if you say these two lines are differing from one another. So in this part, you can say while elongation and while compressing back, the rate of extension and the rate of compressing back is not similar or not the same for this particular elastomer. So you'll say there will be some lagness in between them while extension and while compressing back. This lagness is also termed as hysteresis. So this behavior of elastomer is also termed as hysteresis. Is it clear?
Yes, sir.
So what do you mean by hysteresis? So you'll say the lagging behind property of one quantity with respect to another quantity. In this part, stress and strain are lagging behind with one another while extension and while compressing back. So this particular curve is called hysteresis curve. Any doubt?
No, sir.
Okay, just write it down. So you may write, what do you mean by hysteresis? The lagging behind
So I'm done.
okay, any doubt?
No, sir.
So this is all about this entire chapter, mechanical properties of solids. Okay. So let's start new chapter, that is mechanical properties of solids, a fluid. Any doubt related to this entire chapter? Noor,
No, sir.
you have done assignment?
No, I didn't register to it in
Okay, okay. Mechanical property of,
the assignment. How many questions are there?
for every topic you'll have, I think, 1, 2 or 3 questions.
And until
Then
when do I have to submit it?
1 or 2 day after the class. I think just 1 day after the class.
Okay.
When you submit your assignment, it may come at this junction and I may check from this point directly. Okay.
Okay, sir.
Try to do from next time. Okay. Mechanical properties of fluid. First, What do you mean by fluid? Any idea? What do you mean by fluid?
Fluid is liquid and
Yes,
its molecules are loosely packed
good,
intermolecules, and it has a tendency to flow.
good. You'll say the matter which having tendency to flow is called fluid. Okay, that's it. So mainly we have liquid and gas, both having tendency to flow. So then in this entire chapter, we mainly define for liquid and gas. Since we have in last chapter, we have defined for solids only. In this entire chapter, we mainly define for liquid and gas. Okay. So fluid is matter having tendency to flow, liquid and gas. So to define this fluid, let me define you some basic term. One is density. You must have learned about density. Density is ratio of mass and its corresponding volume. So in case of water, density of water will be maximum at 4 degrees Celsius. It will be equals to 10 to the power 3 or 1000 kg per meter cube. In terms of CGS unit, it will be 1 gram per centimeter cube. So just remember this particular term. Next, may define the next part, relative density. You must have learned about it in your class 9th in chapter gravitation. Noor, any idea what do you mean by relative density?
No, sir.
It is just a ratio of density of any substance to the density of water at 4 degrees Celsius. So you'll say relative density is density of any substance divided by density of water at 4 degrees Celsius. Since in both numerator and denominator having same quantity, so their unit will cancel out each other. So relative density will be unitless quantity. This particular ratio is also called specific gravity. So you can say relative density and specific gravity are same term. Is it clear?
Yes, sir.
Now in this entire chapter, fluid, we mainly divide it into two parts. One is hydrostatics and the next is hydrodynamics. Hydrostatics means study of fluid at rest. Hydrodynamics means study of fluid in motion. Any doubt?
No, sir.
So first we start with hydrostatics part, in which you have to learn about pressure, Archimedes principle, and surface tension and their various application in our daily life. Just write it down.
I'm done. So I'm done.
What is Vandra?
Sorry?
Nothing. Okay. So let's start with hydrostatic part, in which I will define you first pressure related to Pascal's law and its various application. Second, Archimedes' principle. And then most important, surface tension. Hydrodynamics start with flow of liquid. So mainly defined first, viscosity, which is similar to friction, what you have done in chapter 5th, Newton's law of motion. Next, types of flow of liquid, and the most important, Bernoulli's principle, and their various application in our daily life. So first, start with pressure. You must have learned about pressure in your earlier class. Do you have any idea what do you mean by pressure, Noor?
Pressure means the applied force.
Applied force. So what will the use of pressure if we have already force? Since we have force, so we can manage by using just force. So I use pressure. Let me define you. Suppose you have a surface like this, on which you may apply a particular force in different direction. First, along this direction. Second, along this direction. A third, along this direction. So in first part, this applied force to the surface may have some inclination with it, let's say theta. In second part, applied force is perpendicular to the surface. And in third part, applied force is tangential, or we can say it is parallel to that particular surface. So we define a term that is thrust. Do you know what do you mean by thrust?
No, sir.
Thrust is perpendicular force acting on that particular surface. So just tell me which one force in this particular part is perpendicular to that surface?
F3.
F3?
Sorry, perpendicular. F2.
Good. So F2, we can call it as thrust. So thrust is a special name of force which is perpendicular to that surface. Okay? So thrust is perpendicular force acting on surface. So pressure is how much perpendicular force is applied over a particular surface per unit its cross-sectional area is called pressure. So for pressure, we just need thrust. So it states the thrust or perpendicular force acting on a surface per unit area of cross-section is called pressure. So pressure is equals to thrust divided by area of cross-section. Thrust is nothing but force which should be perpendicular to that surface divided by area of cross-section. Is it clear, Noor?
Yes, sir.
Now just tell me the unit of force and unit of area.
Unit of force is Newton.
Good.
Unit of area is meter square.
Meter square, yes. So SI unit of pressure will be Newton per meter square, which is also called Pascal. And this particular quantity is scalar quantity. Okay, just write it down till this part.
Finished.
So fast, mashallah.
I'm writing along with you.
Okay. Now, I'm giving you a question related to this part. A force of 20 Newton is applied on a nail to inject on a surface if area of tip is 4 mm square. Find pressure applied. Just use the above formula, put their values and simplify it, and write each term in their SI unit.
Five Newton per meter square.
Just see this particular term or area, how much it is. It is in mm square. So we have to first convert it into SI unit. I've told you in last chapter how to convert mm square in terms of the SI unit meter square. We have force equals to 20 Newton. Area of cross section is 4 mm square. So how to convert mm into meter? Noor?
10 raised to minus 6.
Good. 10 raised to minus 6 meter square. Now apply the above formula.
If into 10 raised to minus 6 meter Newton per meter square.
Just see, we have pressure equals to force divided by area of cross section. How much we have force is 20. Area of cross section is 4 into 10 to the power minus 6. Okay. So in this fraction, we have two different parts. One is the integral part and the other is exponential part. So I defined you to first solve the integral part. So this 4 will cancel out this 20 in 5 times. So you're left with 5 divided by 10 to the power minus 6, which is in denominator. So how to move this denominator term to numerator?
You have to change the sign.
Good. So what it will become?
5 into 10 to the power 6.
Good. Pascal or Newton per meter square. Any doubt?
No, sir.
Okay. You're done?
Yes, sir.
But in this part, we have to calculate pressure due to fluid. So let me define you how to calculate pressure due to liquid or gas. So next term is pressure due to column of liquid, which is also called gauge pressure, represented by Pg. Suppose you have a vessel in which liquid is filled up to this point. Now, in this particular system, just consider liquid to be one body and this vessel, which is enclosing that particular liquid, to be another body. Okay. Now, just tell me, is there any acceleration of this particular liquid by any external agency?
No.
Is there any force acting on this particular system?
No.
You will say, since whole system must always enter or in influence of gravity, so there will be always gravitational force acting on each object. Okay. Similarly, in this part, this liquid must be attracted towards gravity due to gravitational pull, and due to that particular amount of force, they will exerting some pressure at some depth, this. We have to calculate for this column of liquid how much pressure is acting at this bottom point. Let's say area of this particular base from this point to this point is A, column of liquid of height h, and density of liquid is rho. Consider liquid having density rho in a vessel. So we have to calculate pressure. For that, we need force as well as area of cross section. So how to calculate force? First, mass of liquid, which is equals to density into volume. Density is rho, volume of that particular cylindrical segment, mass of liquid in cylindrical segment. Volume is, how to calculate volume of this particular cylinder? Noor,
Yes, sir.
I think you have learned this particular term in class 10, how to calculate volume of a cylinder. Like this.
Yes.
Pi r square is nothing but area of its base, which is circular in shape. So we can write it at A times vertical length, that is h. So volume of any geometrical figure will be area of base times corresponding height. Is it clear?
Yes, sir.
Now we have calculated mass. So if you have to calculate force experiencing by this much amount of liquid will be mass times gravity. Okay. Put the value of mass to be rho AH times gravity. Any doubt?
Can you explain force one again?
Since this particular liquid must be experiencing a downward force due to gravity, this particular liquid must be experiencing downward force due to gravity. So force equals to nothing but mass times acceleration. And here we have acceleration is gravity or gravitational acceleration or acceleration due to gravity. Is it clear?
Yes, sir.
We have already calculated mass of this cylindrical segment of liquid, rho AH. So if you replace this mass by this term, you will get net force exerted by this liquid at this space will be this much amount. Now for pressure, what we need? Force and area of cross section. So pressure will be force divided by area of cross section. Force is rho AH times gravity. How much area of this particular base is A? So this A and this A will cancel out. So you're left with rho GH. This particular pressure is due to column of this vertical segment of liquid. This pressure is also called gauge pressure. Is it clear?
Yes, sir.
Just write it down.
So I'm done.
Now, in this particular formula, we have three different terms. First is rho, that is density of liquid, g, which is gravity or acceleration to gravity, and next is height. Height is vertical column of liquid. Rho is density of liquid, g is acceleration due to gravity, and h is vertical column of liquid. So from this relation, we may say if liquid is accelerated by any acceleration, it must exert some pressure due to acceleration by that influence. Next, in this particular formula, there is no any information about its direction of acting. So you can call this particular quantity is direction independent. That's why it is termed as scalar quantity. Is it clear?
Yes, sir.
Next, you can say at same depth, pressure will be same in all direction since gauge pressure is independent of direction. Next, in this part, we have density, acceleration due to gravity, and next is vertical column of liquid. There is no any information about how much quantity of liquid will be exerting that much amount of pressure. So you'll say this pressure will be independent of amount of liquid above that particular point. It just depends about vertical segment of liquid present over that particular point and nothing more. Any doubt?
No, sir.
Okay, let me define you related problem related to this concept. First, you can say there is no information about its direction. So you'll say it acts equally in all direction at same depth. Next, it is independent of amount of liquid. It just depends upon vertical segment present over it. Let me define you problem related to this and how to answer it. Suppose in a vessel, liquid is filled up to this point. So at same depth from surface, let's say at this point, H, if you have to define pressure, let's say one of the segment is along this direction, P1. The next segment is at this point, P2. The next segment is at this point, P3. And the next segment is at this point, P4. So you will be asked how these different pressure are related to one another. So you will say at same depth, pressure will be independent of its direction of action. So all these P1, P2, P3, P4 should be equal to each other. Is it clear?
Why are they equal?
Just see in the above statement or first statement, this part. Since in this formula, there is no information about its direction of action. So you'll say at same depth H, it equally act in all direction with same value. So depth is same. So at same depth, pressure will be equal in all direction. That's why P1, P2, P3, P4 should be equals to each other. I will prove this particular statement in Pascal's law. Okay? Or you may define on the basis of this relation also. Since in this particular formula, there is no any information about its direction of action. So you can say pressure will be same at all point in all direction. Any doubt?
No, sir.
Next question will be, suppose you have any conducting tube. Which may have different shape. Like this. Now, if you start filling liquid from in one side to reach at this point, so if you have to calculate at this point P1, this point P2, this point P3, P4, P5. Since depth of this particular point is same in all cases. So if I ask you, in which of these vessels we have maximum amount of liquid? First, second, third, fourth.
They are all connected, right?
Yeah.
They are all one vessel.
This particular arrangement is just connecting tube, which having different shape at its top point. So they may acquire different amount of liquid in it. So you'll observe in second column, liquid will be maximum volume, and in last segment, it will be minimum volume or minimum amount of liquid. Okay. But according to the above formula, for gauge pressure, It just depends upon rho GH. Is there any information in this about how much quantity it should be? So you'll say no. Therefore, pressure at each particular depth will be same since it will be independent of amount of liquid contained in that particular vessel. Is it clear?
Yes, sir.
So P1 should be equals to P2, P3, P4, and P5 all should be equal to each other. So from this, we can conclude pressure equally acts in all direction at same depth, and it will be independent of amount of liquid. It just depends upon three factors: density of liquid, acceleration, and next is height or vertical column of liquid placed over that particular point. Any doubt?
No, sir.
Okay, just write it down.
Sir, done.
Now, the next part is I'm defining all the different part related to this term. Then I will give you different problem, how to simplify it. Okay. The next part is atmospheric pressure. You must have learned about it in class 8th or 9th. I think class 8th. What do you mean by atmospheric pressure?
Pressure exerted by the atmosphere.
Good. It is the pressure exerted by air or atmosphere on all objects living on the surface of Earth is called atmospheric pressure. So pressure due to air or atmosphere on all objects living on the surface of Earth. So next, we have to calculate its magnitude. How much numerical value or how much pressure in terms of number it will equivalent to. So to calculate this particular part, suppose in a vessel, mercury up to this height is taken. Now, next, inverted evacuated tube is inserted into it. A very thin tube is inserted into it like this. Then, suppose at this point A, at this point B, this tube is any capillary tube or very thin tube, which is initially evacuated. It means there is no air inside it. Noor, any doubt?
No, sir.
Now, if I ask you, is pressure at point A and pressure at point B same or they are different?
They are different.
Why?
Because pressure at point uh, B is surrounded by the capillary tube.
No, just think capillary tube is massless tube. There is no any mass of this particular tube. Okay. So how much is pressure at point B and how much pressure is at point A? Is there any pressure at point A?
No.
You will say there must be air all around it. above to this particular point, which must be exerting some atmospheric pressure to this point. Okay.
Okay.
So we have pressure at point A due to atmosphere. And since there is no any column of air above to this particular point B, since it is initially evacuated. So how much is pressure at point B? So you will say 0.
0.
Now, is there any pressure difference between point A or point B? Yes, we have higher pressure due to atmospheric at point A, and there is no any pressure at point B. So higher pressure at point A and lower pressure at point B. Is it clear?
Yes, sir.
Will there be any matter flow from higher pressure to lower pressure? Will there be any movement of matter from higher pressure to lower pressure? You will say yes. Matter flows from higher pressure to lower pressure. So you'll say, due to this pressure difference, there will be a rise in level of liquid in this particular tube, since B having lesser pressure as compared to A. So this pressure difference will create movement of liquid to rise up in this particular tube. And experimentally, it was calculated total amount of liquid raised in this particular column is about 76 centimeter in case of mercury from the surface level. Is it clear?
Yes, sir.
Now, how much is pressure at point B? So you'll say it is the vertical column of liquid, which is in that tube, which must be exerting at point B. So at equilibrium, net pressure at point A must equals to net pressure at point B, so that there will be no further flow from A point to B point. Is it clear?
Sir, the last thing what you said, can you say it again?
I've just assumed, say, this particular condition to be equilibrium. Equilibrium means there is no further flow or further change in level of liquid. So if there is no further rise or fall in level of liquid in this particular tube, so pressure exerted by this particular column at B should be equals to pressure at point A due to atmospheric pressure. So pressure difference between these 2 points will become equal to each other, or you'll say there is no further pressure difference between these 2 points, so there will be no further flow of liquid or rise or fall in level of liquid. Is it clear now?
Yes, sir.
So we can conclude at equilibrium, pressure at point A must equals to pressure at point B. Pressure at point A is due to atmospheric pressure. Let's say this is P0, and pressure at point B is nothing but due to vertical column of which liquid? Noor?
Yes, sir.
At
Can
point B, we have pressure due to which liquid?
the liquid which is inside the tube?
So which is nothing but mercury.
Oh,
And
yeah.
how to calculate pressure due to vertical column of liquid? It is due to by using gauge pressure, that is rho GH. Is it clear?
Yes, sir.
Rho is density. For mercury, density of liquid is 13.6 into 10 to the power 3. Value of gravity is 9.8, and height, that is vertical column of liquid. How much it is it? 76 centimeter. So 76 divided by 100. Is it clear?
So why are you dividing it by 100?
To convert it into meter, since meter is its a SI unit.
Okay.
Now, if you simplify this particular expression, you will get 1.013 into 10 to the power 5 Pascal. And this much pressure is due to air or atmospheric pressure, we call it as 1 atm. Any doubt?
No, sir.
So we may write this particular pressure as 76 centimeter of Hg. It means the vertical column of about 76 centimeter of mercury will exert same pressure which is equivalent to 1 atm or 1.013 in 10 to the power 5 Pascal. Any doubt?
So HD is 1 ATM. What is HG?
Hg is mercury.
Okay.
Its chemical name, hydrogirum. So the pressure exerted by mercury column of about 76 centimeter is equivalent to atmospheric pressure, what we have calculated in this part.
Yes, sir.
Any doubt?
No, sir.
There will be some other unit to find this pressure. One is bar, which is equals to 10 to the power 5 Pascal. Next is millibar, which is equals to 10 to the power 2 Pascal. Next is 1 torr, which is 1 mm of Hg, and which is equals to 133 Pascal. So these are some other unit to calculate pressure. Just write it down till this part. And if you have any doubt, please ask.
Sir, with these 3 different units, we can also calculate pressure.
Yeah. Or you'll be just asked, what do you mean by 1 bar, or how much it will numerically equal to pressure, or in terms of Pascal.
Okay, so we don't have to use it in any question.
Yeah, you have to use only Pascal since it is an SI unit, or SI unit of pressure is only Pascal. So you have to always answer in terms of Pascal.
Okay, I'm done copying.
So we have up to this part calculated gauge pressure due to vertical column, and next is atmospheric pressure. So if you have to calculate how much is the total pressure acting at any particular depth, so you'll say 1 due to vertical column placed over that particular bar, and next the air above that particular point. So net pressure, which is also called absolute pressure, equals to atmospheric pressure plus gauge pressure equals to P absolute. So this will be your combined resultant formula to calculate net pressure at any particular depth. Noor, any doubt?
No, sir.
You're written?
Yes, sir.
Okay. Now let me give you a question related to this part. First is find gauge pressure, absolute pressure at depth of 10 meter in ocean. Suppose this is surface of liquid in ocean, and you have to calculate pressure at depth 10 meter. Let's say at this point. So pressure at this point will be due to this column of liquid plus outside pressure due to atmosphere P0. So try to calculate gauge pressure as well as absolute pressure. Use the formula and simplify it. Tell me how to calculate gauge pressure, or what will be formula for it?
Rho GH.
Good. What will be rho?
Density of the water.
Good. So how much density of water is? I've given at the starting of this particular chapter. Just see.
10 raised to 3
Good. Take the
kilometers.
gravity. Take the value of
9.3.
gravity to be 10.
Okay, 10. So
And we have height of column of liquid 10 meter.
sir, it's 10 raised to 3 into 10 into 10. So the two other 10s will have 10 raised to 1 and 10 raised to 1. So we can do 10 raised to 5. 10 raised to 5 will be the answer. Can we
Good.
do it like that?
Yeah. Now just apply the above formula to calculate absolute pressure.
Sir, we don't know the atmospheric pressure, right?
No, we have just calculated.
That Sir,
Just see this part. This particular P naught.
Okay, so it's constant. Like,
Yeah.
okay.
So P absolute equals to P naught plus PG. We have atmospheric pressure. We have calculated gauge pressure. Just put these two values and simplify it.
1.013 into 10 raised to the power 10.
No. Let me define you. P naught is 1.013 into 10 to the power 5 Pascal for atmospheric pressure. And you have calculated gauge pressure as 10 to the power 5 Pascal. Okay.
Yes, sir.
So there will be always 1 multiplied with this part. Okay.
Yes.
So on adding or subtracting, we just take out common term from each part like this. Is it clear?
Yes, sir.
So if you take out common, you're left with 1.013 from the first part and just 1 from the second part. And 10 to the power 5 is common from these two parts. Is it clear?
The one, how will it come to this side, meaning to 1.013?
Since the value of atmospheric is about this multiplied by this. Okay.
Yeah.
And since gauge pressure is only 10 to the power 5 Pascal, so for each number, there will be 1 multiplied to it. Since 1 is multiplicative factor of all number.
Yes. Okay, sir, I understood it.
So I have just taken out common 10 to the power 5 from both these two terms. So now we have 1.013 in 10 raised power 5 and plus 1 in 10 raised power 5. So 1 plus 1.3 will become 2.013 into 10 to the power 5 Pascal. Is it clear?
Yes, sir.
On adding and subtracting, there will be no change in its exponential. It will remain same. Okay.